Hello everyone and welcome once again to my channel. This time we are going to be looking at a chemistry class on electronic configuration of elements. Now this area of chemistry is very important, especially for those students that would be preparing to write in O-level examinations. Now this aspect of chemistry is very vital, and some students they find this aspect very challenging. So it's with my hope that immediately after this video lesson you should be able to attempt questions with regards to electronic configuration of elements. So what I did was that I just outlined the points that I'll be talking on. The first point is rules of orbital configuration. Then the second point is energy gradation. The third point is orbital configuration of atoms and ions, meaning charged atoms. Charged atoms are called ions. And then focusing on the first 20 elements, all right? Not all of the first 20 elements, but in the series of the first 20 elements, we are going to be looking at some of the elements there. And then orbital configuration of transition elements, just focusing on the 21st all through to the 30th element, talking about scandium all through to zinc. And again, we are still going to look at patterns with which we can use to represent the orbital configuration of elements. Now, of course, we have two patterns. There's two common patterns. We have the expanded and we have the condensed. So let's start by looking at the first point, which is rules of orbital configuration. But before then, when we say orbitals, when you hear the word orbitals, what should come to your mind? They are simply regions or space where there is a high tendency or probability of finding electrons with certain amount of energy. Keyword electrons, or finding electrons. So it means that what you feel in orbitals are electrons and not protons or neutrons. So your major focus should be on electrons. All right. So orbitals are also regarded as subshells. So when you hear the word subshells, just know it's still known as orbitals, or you can call it sub energy levels. Sub energy levels. And taking an overview of orbitals, we have about four main types, and then they are S, P, D, and F. Now, S is called sharp, then P is principal, then D is diffuse, then F is fundamental. So these are the four main types of orbitals. Now, the S orbital has a shape spherical in shape. Then the p orbital is dumbbell in shape. Then the d orbital is double dumbbell. Now you can rename this as dome. Then while the f orbital is complex, the shape is complex. Then the carrying capacities of each of these orbitals. For the s orbital, it can take maximum of 2 electrons. For p, it can take maximum of 6. Then for d, it can take maximum of 10. And F, it can take maximum of 14. So it's very easy for you to get the maximum number of electrons that each of these orbitals can accommodate or they can hold. When you know that the s orbital takes maximum of 2, automatically the common difference amongst them is 4, in that when you add 4 to 2 you get 6. Then when you add 4 to 6 it gives 10, then 4 to 10 is 14. All right. So looking at these orbitals, how can you identify them in terms of diagrammatic representation? Now you must have come across something like this in your textbook, and then you now start seeing things like 1s, 2s, 2p. Now it means that this S is known as this sharp orbital. Then the P there is what? Is principal. Alright. So when you see boxes like this represented using ladder form, of course, that is considered as orbitals. And never should you mistake this for shells. Shells take this diagrammatic representation. This is for shells. Alright. So don't mistake this for this. So on the board, the first point there happens to be rules of orbital configuration. So what are some of the rules that we must obey when we want to get the correct orbital representation of elements? There are about three main rules. And what are they? We have the Hund's rule. The Hund's rule, of maximum multiplicity. The Hund's rule of maximum multiplicity. Then we have the other known as the Pauli's exclusion principle. Then we have the last being Aufbau's, also known as building up principle. Now, what does these principles state? Looking at the first principle, which is the Hund's rule of maximum multiplicity. Now, it says that when you are filling degenerate orbitals, electrons must first be filled singly before pairing can occur. And what does that mean? Now, it's taking our mind to keywords, degenerate orbitals. What are degenerate orbitals? They are simply orbitals that can be split into different parts, such that each part can accommodate equal or equivalent number of electrons. What does that mean? It means that when you have a single box like this is for S, meaning it can only take two. But when you have a box that can be split into three parts like this is for P. When you have a box that can be split into five parts like this is for what? D. Then that of F is seven parts. So what do you notice? The S cannot be split because it can only take two. The P is supposed to be a bigger box like this, but you have to split into how many parts? Three parts, so that each part will take two, two, two to give six. So since you are splitting p orbital into different parts, then of course p orbital is now called a degenerate orbital. From my definition of degenerate orbitals, I said they are orbitals that can be split into different parts, such that each part will take equal number of electrons. So in this case, this is also degenerate. So it means that the degeneracy of orbitals starts from the p orbital, while the only non-degenerate orbital is S. Why? You can't split it. But for p orbital, d orbital and f orbital, they can be split. Remember I said that the s orbital takes maximum of 2, p is what? 6, then d is 10 and f is 14. So it means the number of parts you have to split these orbitals into, meaning the pdf orbitals, because remember that they are the degenerate orbitals. So the number of parts you have to split P into is 3 parts. D is what? Is 5 parts. Then F is what? 7 parts. Alright? So that's how it works. So PDF orbitals are degenerate orbitals. So when you are filling electrons in these degenerate orbitals, you have to fill the electrons singly in this pattern before you now start pairing. So imagine, let's say I'm told to fill 5 electrons in these degenerate orbitals. How would I go about it? I will not just pair instantly like this and then start doing. No. What I would do is I would fill singly before I would start pairing, in obedience to this rule, because this rule is valid to degenerate orbitals. Alright, that's where this rule comes in. So it means if I want to fill 5 electrons, I should fill it like this: 1, then 2, then 3, then 4, then 5. This is for 5 electrons. You got the point now? What about if I'm told to fill 4 electrons? It shouldn't be paired instantly like this, because this will be wrong. So all I will do is to fill singly first, which is 1, 2 and 3, then before I will now pair. That's because I'm dealing with degenerate orbital. If assuming I was dealing with just the s orbital, I shouldn't obey this rule. Why? Because this rule is only applicable to degenerate orbitals. So all I will just do is just to pair instantly. That's for the s orbital, being the only non-degenerate orbital. That's in obedience to this rule. Then what about the Pauli's exclusion principle? Now, the Pauli's exclusion principle has it that no two electrons of an atom can have the same 4 quantum numbers. Now, quantum numbers, I will treat that specially in another lesson. But we have 4 quantum numbers. We have the principal quantum number, we have the azimuthal, we have the magnetic, and we have the spin. I will treat that separately. But one very vital thing that you need to take cognizance of is that there is a particular quantum number that the Pauli's exclusion principle introduces us to, which is considered as the spin quantum number. And it has it that electrons, when they occur in pairs, they are not supposed to move in the same direction. They are supposed to move in opposite directions, meaning the clockwise and the anti-clockwise, meaning that one should be pointing upwards while the other downwards. Alright, so if I have something like this now, let's say this is the s orbital and it wants to take 2 electrons, I should not draw my electrons in this order. Why? Because these two electrons are moving in the same direction. So I should draw it in a way like this, in that one is pointing upwards while the other is pointing downwards. That's coming from this Pauli's exclusion principle. Then what about the Aufbau principle or the building up principle? It is this Aufbau principle that will now lead us to the energy gradation. What does that mean? Now, Aufbau principle, it states that when you are filling electrons in orbitals, you must start filling the electrons in orbitals of lower energies before moving to filling orbitals with higher energies. And what does that mean? It means that it's just like ladder. If you lean a ladder on a wall and of course you want to ascend to the top of the building, now what are you supposed to do? The ladder there that you are leaning on that wall will function in helping you to ascend to the top of the building with ease, meaning you have to start with a step at a time, meaning the lowest point, then you start ascending. That's how the Albert principle is. That's why you see that most times in your textbook, whenever they are drawing that of the orbitals, they usually use that ladder representation, more or less like this, the one I drew previously. So looking at this now, this is like a ladder. So you start filling electrons from this point to this point and to this point. So looking at these three now, the one that is highest here happens to be this. This is known as 1s, this is known as 2s, while this is 2p. So the one with the highest energy among these three now is actually what? The 2p. So when you are filling electrons, according to the Albers principle, you have to start filling electrons from the lowest point before you move to the next and then the next. So that's how it works. All right. So why I said that this Albert principle will lead us to energy gradation is that this arrangement I wrote here is coming from the energy gradation. So I've just been mentioning energy gradation. Then what is energy gradation all about? It's like a profile that will show us on how we can, the direction we have to go with. You get the point now? So what I meant by that is something like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and 4f, 5s, 5p, 5d, and 5f, 6s, 6p, 6d, and 6f, 7s, 7p, 7d, and 7f. So it takes this pattern more or less like from top to bottom. They are moving in the slantness, something like this. Now, if we want to start representing it, now the first one there is 1s. So 1s, this is the first, then the next is 2s, which is this, then the next is 2p before 3s. So 2p, 3s. So you don't have to start cramming this anymore. It is with this profile that you'll be able to get all this. So don't cram anymore. Then the next is 3p, 3p, then 4s. Then the next is 3d, 4p, 5s. So 3d, 4p, 5s, and it continues, it continues. So one very important thing that you need to take note of is that this moving in this direction, it is increasing in this direction. What is increasing there? Energy. Energy increases to this direction. So when you move to that direction, there is increase in energy level. Then coming down to this direction, there is what? There is decrease in energy level. Why I am writing this is because they might bring questions even in exam, and then you might have been, maybe you might have even seen some questions. A, you see options like A, 4p, then B, 5s, C, 3p, and D, 3d. You are being asked which of the following has the highest energy. In this case now, checking this energy gradation profile, you ought to know that the one that is supposed to be having the highest energy should be what? 5s, because energy increases in this direction. Then what about the one with the lowest or the least energy? In this case, it should be what? it should be 3p. Why? You have 3p here, 3p here, then you have 3d here, then you have 4p here and 5s. So it means the one with the lowest energy in this case should be 3p. But among all of them here, the one with the lowest energy is 1s, while the one with the highest in this series now should be 5s, and the energy increases, continues. Alright, so that's how it works. But in a case whereby they did not specify the numbers, there were no numbers attached to these orbitals, it's obvious that you have to go with the generalized principle, which is S, P, D, and F. Since S can take just 2, P is 6, D is 10, and F is 14. So it means a particular orbital, when it accommodates more electrons, of course, there will be more energy because electrons, they move along with energy. So I can as well say, the more the electrons, the more the energy. You understand the point now? All right. So if I say SPDF, which one has the highest energy? It should be F. Then the one with the lowest energy should be what? S. So that's how it works. We are still going to use this energy gradation profile to tackling questions pertaining to orbital configuration of atoms and ions. That will be the next point that we want to look at now. So let's consider the next point, which is the orbital configuration of atoms and ions, and then focusing on the first 20 elements. Now, let's take a case study, sodium. Sodium, Ne. Now, what position can you find sodium when you are reciting your first 20 elements? Sodium is found in the 11th position. Now, this 11 is known as the atomic number of sodium. And if this 11 is the atomic number of sodium, remember that another name for atomic number is proton number. That's another name for atomic number. And if I write sodium in this pattern without writing anything like positive or negative, plus or minus here, then that's to show that this is sodium atom. So no charge, sodium atom. And when you have an atom without a charge, you can call it a neutral atom, meaning no charge, neutral. And any neutral atom, there is one very important thing that you need to take note of. And what's that? The proton number of any neutral atom, the proton number is always the same as the electron number. Remember that what we focus on when we are filling orbitals is the electrons and not the protons. Remember that. So since we can determine the number of electrons via the protons, then it will be very easy for you to get the number of electrons we are working with. So of a neutral atom, I said the proton number and the electron number, they are the same. So since this is sodium atom and this atom is neutral, meaning it does not carry a charge, then the proton number of sodium, which is 11, will still be the same as the electron number. That's what it means. So if the electron number of this sodium is 11, the electron number is 11, then how do we get the orbital configuration of sodium atom? It will be very easy. Remember, we are working with 11 electrons. So how do we go about it? Now, the first orbital here is 1s. So I will draw a small box for it because that s only takes 2. The next, after after the 1s there, you have 2s. So the next is 2s. Then after 2s, we have what? 2p. So P is split into 3 parts. Remember that. So we write our 2p. So that's how it works. Now, we want to fill 11 electrons. So what are we supposed to do? We start from the lowest point here, which is 1, 2. Then we move to the next one, which is 3, 4. Then we move to this, which is 5, 6. But no. This is wrong. Remember, I deliberately failed this one. Why? Because I want to take your mind back to what I previously said. And what did I say? When you get to any P, any D, or any F orbital, remember they are degenerate. You have to obey the Hund's rule. And remember, when you are filling degenerate orbitals, you have to fill singly before you start pairing. All right? So we have to put 1 here, then 1 and 1. And then we'll now come back to fill them up, because remember that this 2 gave us what? 4 in total. So now we are having 6, a total of how many now? 10. So we are still left with 1. We move to the next. What's the next after 2p? Let's check. After 2p, what do we have? 3s. Remember, 3s will still be with a small box. Why? Because of s being small, having just only 2. So what do we have left? 1 electron, because we have filled 10. Remember, it's 11. So 10 plus 1 give us 11. So what are you supposed to do? If you now want to bring out the orbital representation of this sodium, then it should be written as 1s. How many electrons are in 1s? Then you write it as 2 here, which is this 2. 2. Then the next, 2s. How many electrons are here? 2. Then the next, 2p. This should be what? 6. Then while this one is 3s, then we have 1 electron. So this is the orbital representation of sodium atom. Don't forget that. Then what about if you are told to give the orbital representation of sodium ion, meaning Na plus, sodium ion? Remember that plus here implies that sodium has lost how many electrons? It has lost 1. And previously sodium atom had 11 electrons. So instead of this guy having 11, now it has lost 1. So it will now be left with what? It will now be left with 10. So if you are now asked to give the orbital representation of sodium ion, it's different from sodium atom. Why? Remember, sodium atom has 11 electrons, while sodium ion has 10. So how do we go about it? We can still go to this our profile, 1s, 1s, then 2s, then 2p. This should be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Since it's 10, we have to stop here. So the orbital representation of sodium ion should be written as 1s2, 2s2, and 2p6. So a total of what? Of 10. So this is different from this. Hope you got that. So with all this, then there is something else I would need to explain. And what's that? These representations that we just made now, they are expanded. We still have what is known as condensed orbital representation. By condensed, it means we should be working with the proximal noble gases. I want to say proximal noble gases. Now, the 3 noble gases that you should bear in mind are helium, then neon, and argon. Remember that helium has a total of how many electrons? 2. Neon has a total of how many electrons? 10. Argon has a total of how many electrons? 18. So these 3 will be our standard. And how do we work with these 3 as standard? It's very easy. Now, helium being used as a standard, it is only going to work for elements whose atomic numbers are greater than 2 and less than 10. I will explain this. Elements whose atomic numbers are greater than 10 and less than 18 work with neon. Elements whose atomic numbers are greater than 18 at this O level, then you are to work with argon. How can you do that? Now let's see something. Still working with this sodium, then it will be very clear. Let's work with the sodium. This one now is sodium atom. So sodium atom was 1s2, 2s2, 2p6, and 3s1. That was what we obtained from sodium atom. Now, if I am asked to leave this in condensed representation, then how would I go about it? What category does this one belong to? Of course, it's having 11 electrons, and the atomic number is what? Is 11. So what category does it belong to? Does it fall under the helium, the neon, or the argon? Since it is greater than 10 and less than 18, it falls in the category of what? Neon. So what am I supposed to do? Since neon has a total of 10 electrons, all I will just do is I will just start counting from here, which is 2 plus 2 is 4, then 4 plus 6 is what? 10. So I will just remove these entire substances like this. I will remove these entire substances and I will now replace with neon. I will just write neon because neon has a total of 10 electrons. So instead of me to be writing this, I will just detach everything. Since it gave me 10, I will write neon in square brackets, something like this. Then I will now end it with what? 3s1. Both of them, they are the same. But it's just that this is called condensed. This is like the condensed representation, while this one is expanded. So that's how you go about it. anytime you want to go with condensed, just know that elements whose atomic numbers are greater than 2 and less than 10, you can work with helium. Greater than 10, less than 18, neon. Then greater than 18, argon. Okay, let me still give another as an example before we look at the orbital configuration of transition elements. Now, let's take oxygen as a case study. Oxygen atom and oxygen ion. Now, if you are reciting your first 20 elements, what position can you find oxygen? I guess you can find it in what? In the eighth position. Now, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, the eighth position. So it means the atomic number of oxygen here is 8. Can I call it the same as its electron number? Yes. Why? Because this is neutral, no charge. So the electron number of oxygen here is what? 8. Over here, would it be 8? No. 2 minus means it has gained how many? 2. So instead of having it to be 8, it will now be what? 10, being that it has gained 2. So if you are told to give the orbital configuration of oxygen and the orbital configuration of oxygen ion, how would you go about it? Let's quickly look at it. First and foremost, let's go with the expanded. For the expanded, it becomes what? It becomes 1s2. We can just run looking at it this way. 1s2, then 2s2, then 2p4. 2 plus 2 is what? Is 4. Then 4 plus 4 is what? 8. Or if you are not clear with this, then let me use the pattern of representing it so as for you to better understand. Now, this is 1s, this is 2s, and this is 2p. Let's see. 2 electrons here. 1, 2, 3, 4, 5, 6, 7, and what? 8. Remember, we have to fill singly before we start pairing here. So if we bring them out, it becomes 1s. How many electrons are here? 2. 2s, then 2, then 2p what? 2p4. Previously, that was what we got. So 2 plus 2 plus 4 is 8. What about in the case of this one? If I draw the orbitals in this pattern and then I write 1s, 2s, and 2p, then it becomes what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, it's 10 electrons, so it becomes 1s2, 2s2, and 2p6. So a total of how many? 10. You see that it is different. Then what about if I am not told to give the condensed representations? Remember that this is 8. 8 falls under this category. Greater than 2, less than 10. So I'm to work with what? Helium. So and how many electrons does this helium possess or carry? 2. So I will just remove 2 like this and replace this with helium written like this and write the others, which is 2s2 and 2p4. Then in the case of this, of course, 1s2, 2s2, 2p6, a total of how many? 10. So what category does this one fall under? Does it fall in any of these categories? Of course, it is supposed to fall in this category or this category, because if you check now, it is 10. So greater than 2, less than 10 is in between this or this. Then greater than 10 and less than 18. But since it fell as a standard, you can work with neon. You can just put it as neon, being that neon is what? Is 10. You can put it as neon in square bracket. Or you can decide to go with the lower one, which is helium. I can still write helium like this, and then I will now write the leftover, which is 2s2 and 2p6, whichever one it's correct. All right. So that's how you go about filling orbitals of elements. Then before I look at that orbital configuration of transition elements, there's something I would quickly like to touch on, more or less like a question. Now you might be given this type of question that which of the following would have the same orbital configuration? Which of the following would have the same orbital configuration? And then these are the options: A, Na and Na plus, B, Mg2 plus and Al, C, O2 minus and Na. D, Na plus and Mg2 plus. Now you are being asked this type of question, that which of the following would have the same orbital configuration? How can you tell the pairs that will be having the same orbital configuration? It will be very easy. Any pair that would be having the same orbital configuration certainly would be having the same number of electrons. Alright, so it's just like you having A and B. A has a total of 10 electrons, B has a total of 13. Can never have the same orbital configuration. The reason is because 10 and 13 would not give the same orbital configuration. Remember that what do you feel in orbitals? You feel electrons. So if the electrons are the same, of course they will be having same orbital configuration. So let's check. The one that should be having the same orbital configuration must be the pair that have the same number of electrons. So option A. Option A, sodium has 11. Sodium ion meaning it has lost 1. So it should be having what? 10. 11 and 10. This is wrong. Why? Because they have different number of electrons. Then option B. Magnesium ion, which is magnesium 2 plus. Ordinarily, magnesium should be having 12, but now it has lost how many? 2. So it's now left with 10. Then aluminium has a total of 13. 10, 13, different. Then oxygen ion, which is O2 minus. Previously, the previous question we treated, oxygen has 10 in this case. Why? Because it has gained 2 electrons. Then what about sodium? Sodium has, this is 10, while this one is what? 11. So it's wrong. 10, 11 is wrong. Then over to this place. Sodium ion is what? Is 10 because it has lost 1. Magnesium 2 plus, it has lost 2 out of its 12. So it's what? 10. So 10, 10. This becomes the correct answer. They can also bring questions like, what should be the correct orbital representation of carbon in an excited state? Now, carbon has a total of 6 electrons. So if you want to go by filling 6, it should be a small box, and then you have something like this. This is 1s, 2s and 2p. So 1, 2, 3, 4, 5 and 6. So if you check now, if I'm bringing everything now, it should be 1s2, 2s2, then 2p2. So 2, 2, 2, that should give us what? A total of 6. What do you notice? In the 2p, how many unpaired electrons are here? 2. 2 unpaired electrons are there in the 2p orbital. Alright, so 2 unpaired electrons are there. So if you are now asked how many unpaired electrons would be in the 2p orbital of carbon in an excited state, this representation is known as ground state. Ground state. Ground state. So there is still another that is known as excited state. How can you get the excited state? It's very easy. Now, this 2s that is proximal to the 2p, which has the highest energy level here, so it would now lose one of its electrons, meaning one electron will gain enough energy and leap to a higher energy level. So in this case, when it leaps, it means the 2s will lose one of its electrons to the 2p. So at the end, we are going to be having something like this as our representation. Then it becomes 1, then you get. So in this case, this should be 1s2, 2s1 and 2p3. So this is known as carbon in an excited state. That is the orbital representation of carbon in an excited state. So let's see orbital configuration of transition elements. Now, from all the things that we have considered about the first 20 elements, some of the elements we have looked at, there will be slight discrepancy in the orbital configuration of transition elements, looking at the 21st all through to the 30th element. Now I'm going to enlist them. The 21st element is scandium, then the 22nd is titanium, then the 23rd is vanadium. Then the 24th is chromium, then the 25th is manganese, the 26th is iron, 27th is cobalt, then 28th is nickel, then 29th is copper, then 30th element is zinc. Alright, then their respective symbols. For scandium is Sc, titanium is Ti, vanadium is V, chromium is Cr, then manganese is Mn, then iron is Fe, then cobalt is Co, then nickel is Ni, copper is Cu, and zinc is Zn. Now, considering these elements, and we want to obey the principle of our energy gradation profile, all we are supposed to do is just to represent, not to waste much time. Now, how do we go about representing? Now, we can use this energy gradation and then we'll stop at the point where we need to stop. But there is something special about this transition element. Now, there are about 7 properties of these transition elements that every student is supposed to know. And what are these properties? Now, the first property or characteristic of transition elements is that they are all metals. So it means there is no transition element that is a non-metal. So all of them are metals. Then what is the second property? They are located between the group 2 and the group 3 elements of the periodic table. That's one other property. That's the second. Then the third property is that they have partially filled d orbital. That's one of the unique properties of transition elements. They are known for their partially filled d orbitals. All right. Then the next property is that they form colored ions. Next is they form complex ions. Next is they exhibit variable oxidation states. And lastly is that they have the ability to act as catalysts. Now, the formation of colored ions, the formation of complex ions, and the exhibition of variable oxidation states is due to one feature that they possess. And what's that feature? They have partially filled d orbital. What I'm trying to say is that in an exam condition, they might ask you, why is it that transition elements can form colored ions? Or why is it that they can form complex ions? Or why is it that they exhibit variable oxidation state? The answer is they have partially filled d orbital. All right, so take cognizance of that. So let's come back. Now, considering these elements, let's go with scandium. That should be 1s2 if we want to go with this pattern now. So 2s2, you know it's 21 electrons. 2p6, 3s2, 3p6, then 4s2, and 3d1. Yes, if you count these numbers here, you add them up, you are to obtain 21. So this is the orbital representation of scandium. But it is best, even if this 4s in the energy gradation came first before the 3d, it is best to end the 4s and bring the 3d inside, meaning that we are to interchange their positions. The reason is because of the quantum number. The principal quantum number 4 is supposed to come after the principal quantum number 3. I'm going to explain principal quantum number, azimuthal, magnetic, and spin, in fact the quantum numbers generally, in a separate video. But in this video, one thing that you need to know is just like you saying numbers. When you are numbering 1, 2, you get to 3 before obtaining what? 4. So it's best to end it with 4s2 and then you bring in the 3d1. That's why you see that the orbital configuration of transition element is sort of, strange. All right? So don't get it twisted. Now, looking at this, if I bring this 4s2 outside and I bring the 3d1 inside, it means that if I'm having something like this, if I'm tempted to losing electrons, I must first lose the electrons from the 4s before losing from the 3d. So that's the reason why it's important that you should take note of what I did there. That in every transition element, you have to interchange their positions. You must end with the 4s2. That's looking at this series, because we have other transition elements more than this. But looking at this series, you have to interchange the position, end it with the 4s2, so that if you want to now lose electron, you should start losing your electron from the 4s and not from the 3d. Please take note of this. It is very, very important. Then let's continue. So 1s2, 2s2, 2p6. So it means we are just to be increasing this d by 1 due to the fact that after 21 we have 22. So you have to add 1 to it. So 3s2, 3p6. Then we have to fill the 4s2 always first before filling the 3d. So 3d2. Then the next 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d3. So it's just to be increasing it. As soon as you get to chromium and you get to copper, there is something very abnormal that you have to do. And that abnormal thing is, the reason for doing the abnormal stuff is for you to obey the principle of half field stability and fully field stability. It won't be clear now until we look at it. So let's see. For chromium, it should be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d4. So it ought to be written like this. But no, you are not to write it like this, just like the others. But rather, what are you not supposed to do? You are to make this one to be half filled. What does that mean? Remember that this D here, D is to be split into how many parts? 5 parts, something like this. So if it's having 4, which is 1, 2, 3, and 4, and just imagine you are having a fulcrum somewhere around this region. Now, there's every likely tendency of this thing tilting towards this direction. Why? Because of the fact that it is unstable. So for you to make this to be half field stable, then you must put 1 here so that it becomes at equilibrium. In this case, the complete number of electrons are not there because what d orbital can take maximum is 10. But due to the fact that you now have 5, of course, that is half field. You get the point now? So that's the need for you to actually bring 1 from the 4s, and then you end it with 4s1, and then you add it to this to bring about half field stability. That's only to chromium and to copper. For copper is fully field stability, while for chromium is what? Half field stability. So let's continue. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. You know why it is 5? Because this is not 2. So it's tallies. Then next, 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d6. 1s2, there's a reason why I'm writing all these. Then 2p6, 3s2, 3p6, 4s2 and 3d7. Then the next is 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2 and 3d8. Then the next 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, then 3d9. But no, remember what I told you, fully filled stability. If you fill the d orbital now, let's say we split into 5 parts, and you fill this 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, it's still what? Not stable. So for you to get a fully filled stability, you have to lose 1 from here, and you add it to this to make it what? 10. So this becomes fully filled. You get the point now? So the next, 1s2, 2s2, then 2p6, 3s2, 3p6, then 4s2 and 3d10. All right. So looking at these expressions, key things that you need to take note of includes the chromium and the copper. They ended with what? With 4s1. Those are the only two that ends with 4s1. Then while the rest they ends with what? 4s2. Then next, we can get the condensed representation of these elements. How can we get the condensed orbital representation of these elements? Firstly, let me work with a certain element amongst this series, which is iron, Fe. Iron has a total of how many electrons? 26 in a neutral state. So it has a total of 26 electrons. So this is its orbital representation expanded. This one. Let's focus on just iron. With iron, you would understand how to go about the others. Now, looking at this, if you are not told to give the condensed representation, now the expanded is this. then what should be the condensed? Now remember what I told you, that helium is used when it is greater than 2 and less than 10. Neon is used when it is greater than 10 and less than 18. Then argon is used when it is greater than 18. All right. So it means all of these elements, they fall in the category of what? Of argon. All right. Why? Because they are all greater than 18. Then how do we go about the condensed of iron? It's very easy. All we have to do is to count from here. As soon as we get to 18, we detach the entire stuff and then we replace with argon in square bracket. So let's go. 2 plus 2 is 4, plus 6 10, plus 2 12, plus 6 18. So from here, we just remove this entire stuff, We now write A arrow in square bracket to replacing this entire stuff. Then we are now left with what? 3d6 and 4s2. So 3d6 and 4s2. So this is known as the condensed of iron in a neutral state. Then what about if you are told to give the condensed of iron in a charged state of 2 plus and iron in also another charged state of what? 3 plus. Remember that transition elements, they exhibit variable oxidation states. So it could be differences in their charges. You know, oxidation state talks about the charge an element carries or possesses. So looking at this, 2 plus simply means, is there a loss or a gain? There is a loss. How many electrons have been lost? 2. That's for the 2 plus. So remember I said, when you are losing electron, you first lose from the last orbital before moving to the inner one if there is need. So let's see. Iron is like this. So if it's 2 plus, it means these 2 will have to be lost from the 4s. So when you remove these 2, then 4s will not be having any electron anymore. Then you are now asked to give the condensed. From here, you can even get the condensed. All you simply do, you write your A arrow in square bracket, then you write your, would I write anything in the 4s? I can as well write my 4s and put 0 there, or I might just decide not to write it. Then I will now write my 3d6. 0 simply means it has lost what? 2. I can leave it like this for the Fe2 plus, or I can decide to just remove this 4s since there is nothing in the 4s and leave it like this. So it's still the same thing. Then what about if you are told Fe3 plus? Still from here, 3 plus means it has lost how many? 3. So I will remove 2 from the 4s and I will still need to remove 1. Since I have already removed these 2, this guy has disappeared. Then I will still need to remove 1 from here so that it becomes what? A arrow, then what? 3d5. Alright? So that's how you do it. That's how you go about it. So if you know these ones to be their neutral state, so even when they tell you to go with a charged state of that said element, then it will be very easy for you to represent it. This thing is a very, very key thing or vital thing that you must not joke with. That's the more reason why you should settle down and watch this video over and over and over again until you master it. All right. So it's with my hope that with all these explanations that I have dropped, you should be able to attempt questions pertaining to anything with regards to orbital configuration of elements. So we have come to the end of this video. So if you find this lesson very, very helpful, please do well to hit the like button. And if you are yet to be a subscriber of this channel, do well to hit the subscribe button as well. And you should invite your friends to benefit from what you are benefiting from this channel as well, because there are so many videos that are yet to be published on this channel. There are so many things that you would, learn from this channel. That's the more reason why you should be a subscriber to this channel. Then you should turn on that notification icon or that notification bell that is very close to the subscribe button, so as for you to be the first to be notified whenever I drop exciting and interesting videos like this. Thanks for watching once again, and stay tuned as more lessons are yet to come.